Hi everyone, this is Dr. Swaminathan SM. Now we are going to discuss about the topic called lead lag compensators. So review about the previous class, lead lag compensation with the normalization techniques we have discussed. So here we are seeing about the lead lag compensator introduction and lead lag compensator implementation and the compensators applications. So here the lead lag compensator already we discussed in the lead lag compensator, and here the lead lag compensator, the pole zero function, the transfer function can be written as y divided by x is equal to s minus z divided by s minus p. That is nothing but zeros divided by poles. So x is the input to the compensator and y is the output. S is the complex Laplace transform variable. So Z is the zero frequency, P is the pole frequency. The pole and zero are both diapically negative or left of the origin, that complex plane, in lead compensator while in a lag compensator. And again the same thing, lead compensator file y divided by x s minus z1 s minus z2 divided by s minus p1 and s minus p2. So p1 modulus is greater than z1 z2 and p2. So z1 z2 and p1 p2 are the poles and zeros for the lag compensators and the lead compensators. So z1 and p1 means lead compensator and z2 p2 are the lag compensators. So it provides a phase lead at a high frequency. This shifts that's a root locus to the left, which enhances the responsiveness and stability of the system. So the lag compensator provides a phase lag at a low frequency, which reduces the steady state error. That is the main thing. And the precise locations of the poles and zeros, that is depend on both decide characteristics of the closed loop response and the characteristics of the system being controlled. So, however, the pole and zeros of the lag compensator is closed to the together to cause, that is not cause the poles to shift right, so which could cause the instability or slow convergence, since their purpose is to affect the low frequency behavior that should be near the origin. And lead lag implementation, both analog and digital control systems using lead lag compensator. So the technology for the each case it's applying same. So look at this, y is equal to x minus z1 plus z2 x by s and z1 z2 x by s squared plus p1 p plus p2 y by s and p1 p2 y by s in an analog control system. So in analog control system, you look at this, that is y is equal to x plus 1 by s, p1, p2, y, and z1 is set to x plus, so plus or minus it comes vice versa. So following with the activity, we will discuss about the lead lag compensator. So the in analog control, the analog signal, that is control signal, is typically electrically voltage or current and hydraulic pressure. So in case of lead lag compensator, it consists operational, that is op amp, operational amplifier connected to the integrator as well as a weight adder. So if it is needed, you can add. If it is not needed, you can remove the weighted adder. A possible physical realization of a lead lag compensator is shown in figure. Look at this diagram. So plus minus is the input, x is the input, v is the output. So here the op amp minus plus is connected, plus is down grounded. So this is called the inverting, that is amplifier. So here the resistor are plus and minus. So there is left hand side it's a series connection, or RC is a series connection, and right hand side it is a parallel connection. Again one feedback path, that is a resistor feedback path, is given to the op amp. So in digital control, it is a distribution and derivative values for the integral equation, which is differentiating, amplify the noise signal. Since very small amplitude of the noise signal has its high derivatives in its frequency is high, while integrating a signal averages out of the noise. So this makes the implementation in terms of integrators is more stable. And again f of x is equal to a of x plus I b of x. A of x is the real part and b of x is the imaginary part of the single variable function. And again the single variable function, the phase angle is the argument of f of x. So the left hand side is b of x divided by a of x. The phase angle is negative for all the signal frequencies in network. Then the network is classified at the lag network, and the same thing vice versa. If the phase for angle is positive for all the signal frequency in the network, then the network is classified in the lead network. All the rings are positive. So the combinations, the total network phase angle has a combinations of positive and negative for the phase function of the frequency, then it is called the lead lag network. So plus minus comes vice versa, means that is called the lead lag network. So here the feedback control system, that is depending upon the nominal operation, the design parameters for the particular system under an active feedback control, lead lag network calls instability of this poor speed and response time. So this is the applications. So for the applications of the lead lag compensator, it is used mainly in the robotics, satellite control, and automatic diagnostics for in the medical electronics field, and LCD and the laser frequency stabilization and everything. And here another compensator, it is used PI, proportional integration, proportional derivation, proportional integration derivation, or optimizing controllers to improve the system performance like steady state error, reducing the resonant peak, and improving the system response by reducing the rise time. So all these operations can be done by using these compensators used in the cascade compensation techniques. So for further references, I will add some links, that is website links for your further reference. Thank you.